This video is showing when you are factoring quadratics and you are left with two terms. We're going to use difference of squares if it's possible. If you're left with two terms and you have a squared minus b squared, which is a squared is a perfect square, b squared is a perfect square, and you have a subtraction. So what you're looking for is, do you have a perfect square, another perfect square, and do you have a subtraction? If you have a perfect square, another perfect square, and a subtraction symbol, then that means that you can factor this using difference of squares. It factors to the form a plus b and a minus b. Now you can have a minus b then a plus b. It doesn't really matter. But the one thing you have to show is that one is positive and one is negative. To figure out what the a and the b are, what we do is take the square root of a squared. The square root of a squared is equal to a. So whatever the square root of this first term is, the entire term, is your a, and you put it in the front of both of them. Then you take the square root of your b squared, this entire term in the back, which will give you your b value. And you'll put it in the back of each. So over on the side here, I have written out our perfect squares of 1 through 15. So 1 squared, 2 squared, 3 squared, all the way up to 15 squared. We also have to look for variables. If anything is raised to an even exponent, then it is in fact a perfect square. So our first problem is we have two terms, so we're going to look for a difference of squares. Does not automatically mean it will be, but we're going to check to see if it is. X squared is a variable raised to an even exponent, therefore this is a perfect square. 36 is on our list. This is a perfect square. We have a subtraction sign. We have a perfect square, subtraction. Therefore, this is a difference of squares. We can factor this nice and easily. You still always look for your GCF, and on this problem, our GCF is equal to 1. Everything has a GCF. The smallest number is a 1, and these do not have a common letter, so our GCF is 1. So yes, we are still left with a perfect square, and subtraction. So we figure out what our a value is by taking the square root of this first entire term, which was x squared. The square root of x squared is x. Then we figure out what the square root of this entire back term is, which is the square root of 36. The square root of 36 is equal to 6. We now have our first term and our second term. This factors to, we have the first term is x plus the second term is 6. And then we have parentheses, our first term is x minus the second term is 6. This factors to x plus 6 and x minus 6. You can write this as x minus 6 times x plus 6. Moving on to the next one. As you can see, we do not have 3 is not a perfect square, and neither is 48. It's not in our list. But you always have to check for GCF. The smallest number is 3. So we look to see, can 48 also be divided by 3? It can. So right now our GCF is 3. This only has this one term has a letter, this other one does not, so our GCF is only 3. We have to make sure that we do in fact divide our original problem, 3x squared minus 48. We're going to divide both parts by 3. We now have 3 as our GCF on the outside of the parentheses. We're going to have x squared minus 16. And that was the end of the GCF, so we close our parentheses. Now we look inside the parentheses and ask ourselves how many terms we have. We have 2 terms inside the parentheses. So we look to see if it is a difference of squares. X squared is a perfect square. 16 is a perfect square. And we do have a subtraction sign. Therefore, we do have a difference of squares, and we factor it the same way we just did a moment ago. We figure out our first term, which is we take the square root of x squared, which is equal to x. Then we figure out their back term, which is the square root of 16, which is equal to 4. We now have our first term and our second term. Our GCF still remains on the outside of a parentheses. we have our first term x plus the second term 4, close parentheses. Then we have parentheses, we have our first term x minus the second term is 4, close parentheses. This is finished. We no longer have any exponents inside the parentheses. These are linear binomials, therefore we cannot factor this any further. If we move on to number 3, again 12, we have two terms, so we look for a difference of squares. We have 12, which is not a perfect square, but we always must look for the GCF. Everything has a GCF. Our smallest term is 12, so what we do is we look to see if 12 can go into 75. 75 divided by 12 is not a nice clean number. So then we figure out the factors of 12. So we know it's 1 and 12, 2 and 6. 6 is the next one. 75 divided by 6 is not good either. Then it was 3 and 4. So 4, 75 divided by 4 is not good either. Then we went to 3, 12 divided by 3, 75 divided by 3, it is good. So our GCF so far is 3. 12x squared, 75, there's only one term with a variable, so our GCF is only 3. So I'm going to rewrite the problem of 12x squared minus 75. We're going to divide both terms by 3. We're going to have 3 on the outside. 12x squared divided by 3 is 4x squared. Minus 75 divided by 3 is 25. Close parentheses because that's the end of the expression. Now we look to see if we have a difference of squares because we have two terms. Two terms, we look for a difference of squares. We have our first term is 4x squared. 4 is perfect square, and so is x squared. So this entire first term is a perfect square. 25 is also a perfect square. So we do have a perfect square, and we also have a subtraction sign. Therefore, this is a difference of squares. So we can write out our answer as we take the square root of 4x squared. The square root of 4 is 2. The square root of x squared is x. So our first term is 2x. Then we take the square root of 25, which is equal to 5. So we have our first term and our second term. Our GCF will again still be on the outside of our parentheses. We have our first term is 2x plus our second term is 5, close parentheses, open parentheses. Our first term is 2x minus our second term is 5, close parentheses. These are now linear binomials. And we already have our GCF out, so this cannot go any further. This is factored form. This last one, we're going to look to see if we have perfect squares, but we also need to look for our GCF. GCF. Everything has a GCF, and we must always find it. The smallest number is 4. 25 cannot be divided by 4. Then we also have 2 times 2 gives us 4. 25 is not divisible by 2. 25 is in fact divisible by 1, so our GCF on this case is 1. Since our GCF is 1, we do not need to worry about writing it down because it does not change the numbers. So now we look to see how many terms we have. We still have 2 terms. We want to try and look for a difference of squares. We do have a perfect square, 4x squared again. We do have a 25, which is a perfect square, but this is an addition sign. This is not a difference of squares. Because of the subtraction sign, we cannot do anything else. Now, because our GCF was 1, and it could not factor any further, this is considered prime. Prime. Prime is when it is not factorable, but with the GCF of only 1. Not factorable, but it has a GCF with GCF is equal to 1. If it has any other GCF, then it is in fact factorable, so it's not considered prime. So if the GCF, like on this one, was 3, and we couldn't go further, then it is factorable, but only with the GCF. Now, a sum of squares, which was that a squared plus b squared, just like this one up here, because he had 2 perfect squares and a plus sign, cannot factor except for the GCF. If, this is what I was just talking about, if you factor a GCF, it is not prime. This one was prime because the GCF was 1 and you could not factor it further. So that's why it was prime. If you can factor out a GCF other than 1, then it is considered factorable. This was difference of squares.